But let's assume it wasn't that clear cut. Let's assume we need to do math. Math. I don't know why I say math like a sheep vine. Math. Yeah. But I do. Again, we pull up our equation, delta G naught prime equals negative RT ln KEQ. Or if you don't want to learn a new equation, you can pull up your normal equation, delta G equals delta G naught prime plus RT ln Q. And just remember that you're setting this to 0 because we're talking equilibrium. The math is totally the same. Do it however you want. I don't really care. This is probably easier, I think. And we'll put in what we know. The delta G is positive 29.7 kilojoules per mole. I can spell mole. I can. Negative, that's fine. Ln is going to be fine. KQ, I don't know. That's what I want to figure out, I guess. What did we say the temperature was? 298 Kelvin. We're going to be in Kelvin. And we need an R value. And the problem is, you may have learned R in all sorts of different units and nomenclatures and whatever we're dealing with. Here's the one that's going to be useful to us. R equals 8.314 joules per mole times Kelvin. Because we're dealing with Kelvin, we're dealing with joules, and we're dealing with moles. So let's get it. Ooh, wait. Shit. This isn't joules. This is kilojoules. Another way to think of this that might be more useful is 0.00831 kilojoules per mole times Kelvin. Or you could put in 1,000 scaling factor every single time. Or you can be exceedingly lazy, like a biochemist. Because, pro tip, if you haven't heard this from me enough yet, we like to take shortcuts. We like to make things work. And so why don't I calculate that once? Because, that's never going to change. And that's never going to change. We just defined this as constant. So why don't I just, instead of learning them individually, why don't I multiply them once and figure out what they are and just use that? And it turns out that's 2.48. Try it. You can put in 298 and that guy and get it. I'm not pulling the wool over your eyes. 2.48, which to me is close enough to 2.5. So in my mind, I just use 2.5, which is a really easy number to remember, right? 2.5 or something. And 2 and a shop accident. And just use that every single time and not bother trying to calculate it. And if you ever use that on quizzes and stuff, it'll be fine. Well, let's check. We have Kelvin here. Sorry. So this one's in kilojoules per mole times Kelvin. Temperature is 298 Kelvin. Kelvins cancel, and you're left with kilojoules over moles. So 2.5 kilojoules per mole is our RT. You can put in the numbers yourself every time, and I don't know if you've noticed on the quizzes, I already provide R and T. I've been doing them on every quiz. You can do that, but to me, 2.5 is a lot easier to memorize, and it's close enough for government work. Or you can do 2.4778 if you really it kills you inside. Whatever. But we can get that value. So let's do that. 2.5 ln KEQ. Okay, algebra time. I'm going to divide both sides by negative 2.5. Those cancel out. I need an adult with a calculator. Negative 11.88. And it's unitless now. Because this is kilojoules per mole. This is kilojoules per mole. It's totally unitless. Equals ln KEQ. We've talked about how to get rid of logs a lot. How do you get rid of a ln? E. E to the that, E to the that. That cancels out. And I end up with KEQ equals E to the negative 11.88, which is 3 times 10 to the negative 6. That's negative. Good stuff there? Good so far? KEQ equals 6.3 times 10 to the negative 6. But remember, KEQ is reactants, or excuse me, products over reactants. KEQ is always products over reactants. So when you've got this negative exponent, there's two ways you can convert this into a fraction. One way is to just divide by 1, because that's the identity. You can always do that. 6.3 times 10 to the negative 6 over 1. For every one reactant, there's a millionth of a product. That's valid. The other thing you can do with exponents that's cool is flip the sign. 1 over 6.3 times 10 to the 6th. These are the same number. Right? We just flip the exponent to flip it to the other side. One product for every 6.3 million reactants. Roughly 10 to the 6th to 1. Almost 10 to the 7th to 1. Good stuff? Notice this fits our reality port. Fits to reality. If this reaction is very unfavorable, high positive energy, very unfavorable, even as this stuff starts to build up, it ain't going forward, it's unfavorable. To actually get it to squeak forward, you need millions of reactants to squeak one product through. It's unfavorable, it's not spontaneous. It is hard to make work. And that's what that means. We can relate real concentrations of things to some like vaguely defined energy term. And I think that's really cool. That good so far? Let's try one actually doing the clicker along the same veins, but going the opposite way. Maybe. Why isn't my slide advancing? My computer frozen? Maybe. Click. There we go. So here's doing kind of the opposite thing. If I have the metabolic intermediate fructose 6-phosphate being converted in a reaction to glucose 6-phosphate, and please forgive me, this is not my style. That should be a double-sided arrow, of course. Chemical reactions are reversible. We can find that it has a KEQ of 1.97. So what's our, Jesus. Okay, I'm gonna fix the slide, I can't take it. It's killing me. Two things that need fixing. One, oh, that's not fixing. One, this is a double-sided arrow. But two, I forgot my prime. Killing me. What would be the delta G not prime? See if you can figure this out with your neighbor and get the same result and click on it on in. Math. Anyone feeling like they need a pointer to where to start? It's okay. That's why we're here. So yes, calculator error. You looking for me, Nikki? Oh, well, fine.
I'm sorry.
All right. Many of us have clicked in, but not everyone. So I'll give everybody just a minute longer to think about it. See if you can talk to your neighbor. If you're stuck, it's great to reach out to a neighbor. Tell them you know, but you just want to see what they know. All right, almost everyone has clicked in. Let's see where we're at. There we go. Yay! We can do algebra. Yeah, the correct answer should be negative 1.681 kilojoules per mole. So let's dig into that for just a second. Let's reality check ourselves. The KEQ is 1.97. Remember that you can always divide a number by 1 without changing it. So, for every 1 reactant, I have almost 2 products. It's favorable. Products are favored. So it better be negative because it's favorable. It favors products. So we know it's got to be a negative answer. And then we just have to do the math to find out exactly how much. With time, you can start to get a feel for like how much energy is how much product. And I want to get into that because ultimately, I don't really care about your algebra skills. I don't mean like that in a mean way, but I mean, I want you to be biochemists, not algebraists. So I want to build the intuition. The intuition of what's right and what makes sense is way more important to me than like sig figs on a calculator. And so what I want to do is give us a 5-minute break, because we need it, and then teach you a trick for estimating these without doing any math at all. So 5-minute break, stretch, do what you got to do. It's primal screen therapy. Sorry, wait, what? Yeah, so this, here, let me. This part is unitless because it's molar over molar, so the units cancel. This part is in kilojoules per mole, so the whole thing is in kilojoules per mole. This is in kilojoules per mole, and this will be in kilojoules per mole. So kilojoules per mole plus kilojoules per mole, it's all kilojoules per mole. What? R is 8.314 joules per mole Kelvin. And then when you multiply that by 298 Kelvin, you lose the Kelvin term, and you just get joules per mole. Divide it by 1,000 to get kilojoules. So another way to write this in here is 0.008314 kilojoules. Good question. You look deep in thought.
Yeah, sorry.
That's okay. About this class or about like life in general?
No. What I was thinking about is like, so with the fact that like your KEQ is like 1.97, but obviously you said that the G0 prime is under standard conditions.
Yep.
And we find that as a 1 molar of everything.
Everything's starting at 1 molar, and then the reaction happens. There's what I
okay. Okay.
Like in the tube, you poured 1 molar of fructose 6-phosphate and 1 molar of glucose, and then you waited to see where it ended up, and that's where it ends up.
With that KEQ.
With that KEQ.
But then, if you put it back into products of reactants rather than KEQ, wouldn't you just have 1/1?
If you don't mind, once people are back, I'm going to hit this point because I
Okay.
think it's important, and
Okay.
I didn't do a good job, so we're going to go there.
Okay, cool. Sounds good.
Of course it is good.
CHS. My sister uses
But I couldn't bring it to
every day.
I don't know, I mean, I like, honestly, like, I should really get a camera, like,
Oh, the arrows.
and I have 46
Wow. I used to play Words with Friends. I'm good at that. And then I found out my mother-in-law was cheating. I'm like, what's the point?
People would just like stop and
the,
stare
like,
when he was
really
like,
helpful, like, ties
No, I don't mean like that kind of cheat. I mean like she was really going online and like,
get up and what?
there was a tool where you could type in what letters you had and it would give you the best letters. And I'm like, why? I'm just playing it on the computer now. Like,
Yeah.
what's the point?
Yeah, I don't know, this is, yeah, this is fun, but yeah, I find that when I play, I'm trying to use them. Like, I start to. So I just play around keywords.
That's cool.
I don't know how, like, the system, if it's actually taking into account, like type ones or
Yeah.
how much better they
Skill
are than
range.
others.
Yeah. All I know is whenever I play chess, I try to castle.
Yeah, absolutely.
Yeah.
Even when it's not the wise strategy to do
I
it.
love, I love the nice, that's my, you know, working together.
Yeah,
So the
yeah.
first thing that I did
But it gets
was, I mean, honestly, I just put my calculator, so you have to know
It's amazing how
so like it could be over one, like.
Sometimes.
Or
Wow.
it's really fast. It doesn't-
All right, should we get started again? Has it been 5? I lost track.
Right, exactly.
I'm going to call it 5.
Exactly, so now if we can-
All right. There was a good point raised that I didn't hit quite enough, and I really want to not leave confusion on this. So let me point out there's a disconnect here that we need to be clear on. I just said that this whole delta G not prime thing means 1 molar everything. And then I said, hey, look, you've got twice as much product as reactant. And that seems to not match. And so let me amend, let me try to fix, and add 1 mole of everything at the beginning. That is, I pour 1 molar of this into a test tube, and I pour 1 molar of this in a test tube, and I sit and see what happens. And what happens is at equilibrium, I have twice as much glucose 6-phosphate than I did fructose 6-phosphate. So this kind of tells me what I did in my test tube. I poured in 1 molar of everything, and then a reaction happens and goes to equilibrium, and this equation tells me when all is said and done, where did I end up? Does that help?
So when you're saying the natural log of products of a reactants,
The
you're saying
final
the final
concentrations.
one.
Yeah.
Got it.
Yeah, the KEQ, the products reactants we're talking about when all is said and done.
Cool.
Good stuff. Okay, so there's this relationship then between our delta G and how much product and reactant we get. And that could be really useful to know in terms of like, I put numbers in my calculator, do they make sense? Because it's easy to make calculator errors. So I learned a trick in grad school that made me like kind of like throw up my hands in disgust and be like, why didn't I learn this earlier? You know, nope, broke that one. Seriously, wow. To keep this in mind, and I find it very, very helpful, and maybe you will too. I think some people are like, yes, it works, and some people are like, that makes no sense, I'm just going to use my calculator. That's okay, we have different strategies of learning. But here's my strategy. Every 6 kilojoules per mole of delta G is about 1 order of magnitude in